Welcome, policy advisors. Let's get right into it. You know as well as I do that as researchers in AI evaluation, we're seeing a massive gap between the sweeping industry hype and the hard data you actually need to do your jobs. We're constantly hearing these big claims about AI automating vast sectors of the economy, but let's be real. You simply can't base regulatory frameworks on press releases. In this explainer, we're going to unpack a completely groundbreaking methodology from researchers at Meter that fundamentally changes how we measure AI. It's called the time horizon paradigm, and it moves us away from static test scores and directly towards measuring exactly what matters to you, real-world economic utility. Here is our roadmap for today. We're going to cover the AI benchmark illusion, the time to complete metric, scaffolding and token budgets, humans versus AI models, the human sourcing challenge, and finally, forecasting for tech policy. All right, let's dive into section 1, the AI benchmark illusion. So developers absolutely love traditional synthetic benchmarks, things like GPQA or the ARC challenge. Why? Well, because they're cheap, they're super easy to scale, and boom, you get a quick accuracy score. But we really have to contrast that mechanistic evaluation against real human-led evaluations, which are honestly the only way to measure actual economic utility. Traditional tests are entirely accuracy-based. They just ask, can the model answer this static question? But these benchmarks saturate incredibly fast. A model hits 100%, we build a harder test, and the cycle just keeps repeating. It tells us an AI is quote-unquote PhD level in theory, but when you ask it to do a useful, multi-step job, it completely falls over. Real-world utility requires a totally different lens. We need to know, is the model functionally capable over a prolonged span of time? Cognitive scientist Melanie Mitchell really hit the nail on the head here. She points out that these traditional benchmarks suffer from severe foundational vulnerabilities. The tests literally leak into the training data. The models use approximate retrieval instead of actual reasoning. And honestly, the most alarming part? They find these lazy shortcuts to get the right answer for entirely the wrong reasons. They just lack basic robustness. If we base legislation on these fragile scores, we are basically building regulatory houses on sand. So, that brings us to the core question of our briefing today. How do we actually forecast AI's real-world economic impact? If these static exams are just an illusion, what's our ground truth? Well, the answer lies not in how smart a model appears on paper, but in how much actual, measurable human labor it can successfully replace. Which leads us perfectly into section 2, the time to complete metric. The researchers at Meter have completely re-engineered the evaluation axis, and it's a truly groundbreaking shift. We now evaluate models on a unified axis of human labor time. So instead of asking, did the AI pass the bar exam, we're asking, can this AI successfully complete a task that would take a competent human professional exactly 15 minutes to do, or 2 hours, or maybe 10 hours? This metric, human time to complete, gives us this unified, interpretable baseline to track AI progress. It finally translates all that abstract tech jargon into a metric that economists and politicians can actually use. The ultimate benchmark here is what we call the new employee test. Think about it like this. Imagine you're hiring a human contractor. They're brand new to your specific company, but they already have all the right background expertise from their field. They don't know your specific internal software quirks yet, but they know the domain inside and out. If an AI can reliably step into that exact role for a task that takes a human a few hours, well, now we have a highly economically relevant measure of capability. Moving right along to section 3, scaffolding and token budgets. You see, you can't just drop a raw language model into a job and expect it to work. We have to establish an operational environment, which researchers often call scaffolding. This basically means giving the agent a basic terminal, just like a human engineer would use. But crucially, they found they absolutely must provide explicit operational parameters. They have to give the agent a strict token budget, which is essentially its computational currency, and then constantly feed it real-time signals about how much of that budget it's spent. Without these real-time budget signals, the models totally panic. It's literally like a college student cramming the night before finals without a clock. They just submit half-finished garbage because they have absolutely no concept of pacing. This really highlights the massive gap between human intuition and AI rigidity. When a human manager hands off a task and casually says, "Hey, I'm excited to see your results tonight," a human instantly understands those implicit constraints. They know they need a quick first draft, not some polished multi-day masterpiece. AI has zero implicit context. It requires explicit, hard data, like you have used exactly 1% of your token budget, just to calibrate its effort and figure out how deeply it should search for a solution.
Let's dive into Section 4, Humans versus AI Models.
Let's look at a direct case study benchmarking human baselines against AI performance. Think of this as an unfolding narrative of capability. We start with a trivial 5-second task, locating a specific SSH key in a messy file directory. Models succeed almost perfectly here. Now give them a 15-minute task, like computing basic statistics on a CSV file, and they still do reasonably well. But push them to an extreme 15-hour challenge, like designing a masked language model from scratch, without using specific mathematical operators just to prevent them from copying internet tutorials, and current models hit their absolute breaking point. They fail drastically. Looking at the data, performance drops off along this brutal, steep logistic function. Success is near guaranteed for short, well-specified tasks, but as that human time-to-complete requirement increases, the AI's ability to maintain context, correct its own errors, and navigate ambiguity completely plummet. Okay, I want you to mentally circle this metric. This is arguably the single most important number for your policy frameworks. We define a specific AI model's time horizon as the exact point on that performance curve where it has a 50% probability of successfully completing a given task. So, if a model has a time horizon of 4 hours, it means if you give it a basket of tasks that take humans 4 hours to do, the AI is going to succeed on exactly half of them. All right, Section 5, the Human Sourcing Challenge.
Now, building these benchmarks is incredibly difficult because to figure out how long a task takes a human, you actually have to go hire humans to test it. And amazingly, researchers sometimes found a negative correlation between a person's official years of experience and their actual performance on the benchmark. I know, it's wild, but highly credentialed individuals often underperformed compared to researchers' direct, culturally aligned networks.
Sourcing diverse human baselines is just plain messy. Human intelligence relies heavily on tacit knowledge, the unwritten rules and past context of how things are done. AI relies purely on what we explicitly specify in the prompt. Furthermore, researchers have to avoid adversarial selection. Basically, we can't just pick weird trick questions to purposefully break the AI. To actually be useful for you in policy, the task distribution has to reflect real average economic utility. And to do that, they have to average out the wild variance in human speed using log-normal distributions. Finally, Section 6, Forecasting for Tech Policy. We absolutely must watch these trend lines carefully. Right now, models are relatively competent at tasks taking a few hours, but extrapolating from 10-hour tasks to multi-week or even 1-month tasks, that signals a massive shift in labor dynamics. A 1-month task isn't just cleanly typing out code. It involves the messy reality of ambiguity, course correction, and actual on-the-job learning. If an AI masters that, we are literally in a completely new economic era. The implication for tech regulation here is crystal clear. As advisors, you've got to stop looking at traditional test scores. Please, do not base policy on whether an AI can pass a medical exam on paper. Adopt time horizon metrics instead. You absolutely must monitor when models gain the ability to handle ambiguous, long-term tasks and track their improvements in autonomous error correction. You really need to prepare your labor and economic frameworks for the exact moment AI reaches human equivalents on week-long or month-long horizons. So I'm going to leave you with this final thought to deeply consider before your next committee meeting. The line on the graph is moving steadily to the right. When autonomous agents can reliably execute a month's worth of complex economic labor entirely on their own, is your regulatory framework ready for that new reality? Thank you so much for watching this explainer, and I really hope this framework helps guide your upcoming decisions.